This is just going to be a basic work energy problem just to get us started. So this is 14-3 out of the Hibbeler textbook. I think it's the 15th edition. And it says that the crate, which has a mass of 100 kilograms, is subjected to the action of the two forces. If it's originally at rest, we want to find the distance it slides in order to attain a speed of 6 meters per second. The coefficient of kinetic friction between the crate and the surface is 0.2. All right, so on this, the first thing we want to do is let's draw our free body diagram and kind of figure out what forces are going to do work. All right, so if you look at the picture, here's our crate, and notice we've got this force being applied, and then we have this tension in the cable. It's kind of being used to pull it along. So now, looking at our diagram, let's just draw a box like that, and then we've got the 800 newtons here and 30 degrees, and then over here we've got this tension, which is 1,000 newtons, and then that's at that 3, 4, 5 triangle. All right, now notice it says that we've got friction in here, so we need to include that. So if we're pulling it to the right, notice we've got, this force obviously is going to be moving this way. So friction is going to go in the opposite direction, so it's going to go like that. And we need to put that on here. So here's friction. Remember, for friction, you're going to have your coefficient of friction times your normal force. So for this case, we're going to have 0.2 times N. We'll find N in just a minute. Now N, like we were talking about, is the normal force, so that's just going to go straight up right here. And then last thing we would have would be the weight. All right, so it's going to be 100 times 9.81. And that's what we've got. All right, so first, in order to get friction, I need the normal force. Let's go ahead and calculate that, and then we'll look at what's doing work. So to find this, let's just look in the y direction. Up's positive, so we're going to have an N, and then minus the weight. And then this has a y component, as does this. So let's just start here on the 800. It's going to be a negative 800 sine 30, because that would be that component right there. So negative 800 sine 30. And then this one over here, well, that's going to be a positive y component. So we're going to put plus 1,000. And then we've got that 3, 4, 5 triangle. So to get the component, we're going to multiply that by 3/5. All right, so we've got that, and we're going to set it to 0 because there is no motion in that y direction. Now, if we go through and solve, we're going to get 781 units here would be newtons. So that's our normal force, and we'll be able to use that right here when we do our friction. So now let's look at what forces do work. And remember, in order for a force to do work, you have to have the force and displacement in the same direction. Whoops, started writing what I was saying. So let's look and see. We know our displacement is to the right, horizontal direction. So does gravity here, does weight produce work? No. Same thing with the normal force. These two are not doing any work, because we are not just having displacement in the y direction, Our displacement is totally in the x direction. That means friction's going to do work because friction's in the x direction, It's in the opposite direction of displacement, but it's still in, the horizontal direction, And then we're going to have this component here. That's going to do work. So let's just put the 1,000 Newton force, and then same thing with 800, because again, there's that x component. So let's put 800 here. Now, we've got that figured out. Remember, for work energy, we're going to be using the equation U equals delta T. At least that's the notation for the Hibbeler textbook. So let's go ahead and find U. That'll be the total work. So remember, it's force times the displacement in the direction of the force. Okay, so let's go ahead and find that, and then we'll set it equal to delta T, which is the change in kinetic energy. All right, so U is going to be the forces that do work, So we're going to let's look at 800 first. So we've got the x component of this force. It's 800 cosine 30. That's in the x direction, so that'll be our force. So let's write 800 cosine 30. And then I need the displacement in the direction of that force component, right? So the x displacement. I don't know what it is, right? That's one of the things, that's what we're looking for basically. So let's just call it delta x, right? Because delta x is what we're looking for. Now we need to look at the sign. Is it positive or is it negative? Now, if we look, the force component is going to the right and our displacement is also to the right. So if they're in the same direction, this is going to be a positive, right? So that'll be a positive work right there. Now, let's look at friction. Notice friction's to the left. And the friction force is 0.2 times the normal force. The normal force is 781, so let's put all that in here. So 0.2 times 781. And the displacement, again, we don't know. It's going to be delta x. Now, should this one be positive or negative? Because our displacement is this way, but the force is this way. Since they're in opposite directions, this is going to be negative, right? And then last one is going to be this x component right here. So that's going to be the 1,000 times 4/5. And the displacement is still at delta x. And this one will be positive, right? Because the displacement is this way, and then our force component is in the same direction. So that'll be a positive. And then you can go through and simplify all of this. So if you do that, you're going to end up with 1,336.62 delta x. And then now we can take that and set it equal to delta t. Remember, delta t is the change in kinetic energy, right? So U is delta t. And remember what delta t is. It's 1/2 times the mass times your final velocity squared minus your initial velocity squared. So now we just basically need to put U on the left here. It's 1336.62 delta x. Set it equal to 1/2 times the mass. The mass was 100. And then we need our velocities. So let's go back up and look at the velocities because I don't remember what they were. Okay, so first it's originally at rest. So that means V1, our initial speed, is going to be 0. And then it wants to attain a speed of 6 meters per second. So this is going to be our final speed. So V2 will be 6. So with that, I can put 6 squared minus 0 squared. Right? And then we can simplify that right side. And that's going to give us 1,800. So now you can divide and get delta x, which is 1.35 meters. All right, so now you found your displacement and you were able to use work energy to do it. Now you could also do this same problem using Newton's second law, right? This just gives you another method. So you might think this one's easier than doing Newton's second law. Okay, so that was just a short work example. I will see y'all again for another example next time.